Okay, so it is a great pleasure to have with us today Konstantina Boutsia. Konstantina did her undergraduate at the University of Athens, and then she left Greece to the beautiful Rome and Italy, where she did her master's and her PhD, studying the properties and variability of the AGN. And then after spending some time in Italy and in the US, she moved down under to Chile, where she is currently επιστημονικός επιμελητής οργάνων in Magellan Telescope. I'm not sure how you confuse me.
Instrumentation scientist.
Instrumentation scientist is much nicer. So Konstantina is going to give us a seminar today, and we all look forward to her talk. Konstantina, if you want to share, let's see how things work.
Okay. Thank you very much for the introduction. So today I'm here to discuss with you the contribution of AGN to the reionization, and also give you some highlights of the QUBRICS survey that I am part of the group running the QUBRICS survey in the last 4 or 5 years. So here are part of my collaborators. They are all from Italy, as you can see. And so I start with the talk. So today, what we want to study is the epoch of reionization. So what is this? The reionization is a transition phase in the history of the universe, where from opaque and full of nitrogen hydrogen, it became the mostly transparent medium we see today, with the ionized intergalactic medium that we have today. So one great question that we think that we are answering in the last years is, when did it take place? So based on Gunn-Peterson troughs, they suggest that the reionization ended at a redshift of 5.2 and between 5.2 and 6, which means that it was a very late process. And based on Planck results, suggest that it was also a very rapid process. Everything happened in a delta redshift of 3. The consistent picture that has been arising is of an ultra-latent fast reionization that was practically complete at a redshift of 5.2 and 5.5. So the debate currently is the sources of the reionization. The story goes, and what has been thought in the past, is that the apparent number density of bright quasars and AGN is rapidly decreasing at a redshift above 3. So at the same time, and in the same redshift range, the number of faint galaxies, so the luminosity functions are steep, so we have a great number of faint galaxies. And this means, and the simulation were indicated that they should be the dominant contributor of the reionization at the redshifts above 3. But here there is a caveat. So in order for star formation galaxies to keep the universe ionized, all of them down to an absolute magnitude of -13, they need to have a very high escape fraction. So recent simulations presented by Naidu in 2020, they show that by considering the steep luminosity functions of the galaxies, here there are, we show in the cyan is the Filkenstein, and in yellow is the Ishigaki. And both of them, in the Filkenstein, they assumed an escape fraction which is progressively increasing when we go to fainter galaxies. And we see that this is producing a very, very long process. Like we see that we reach the 0.8 fraction, neutral fraction at a redshift of 11. And with the Ishigaki, it was a unit and by having a constant escape fraction of around 17 for all galaxies, again, you need to reach a redshift of above 9 in order to have the neutral ionization fraction above 8. So 0.8. So all this only based on ultra-faint star-forming galaxies, the ionization process is too long. And Naidu, in order to fit the observational constraints, that here they are the green points, he had to, it required to add bright and rare sources in his simulations in order to match the data. So this opens the door for AGN to be also major contributors. So we need to calculate the ionization rate. In order to see to verify the possibility of AGN contributing, we need to put robust constraints in mainly in two quantities. So first, we need to know very accurately the luminosity function, like their abundance at low luminosities in a redshift range between 4 and 6, and also their typical escape fractions of ionizing photons. So starting from the escaping fraction, Cristiani et al. In 2016, they have calculated the escape fraction for bright quasars from the BOSS survey. So here I show the method, and as you can see on the left side, I don't know, can you see my cursor? Can I point? No, I can't.
I cannot see the cursor, but
okay, it's fine. So I will describe. So on the left panel, there's the continuum. The red light is a fit to the continuum, and then this is the left panel of the left plot. And then on the right panel, so this continuum, by multiplying with the expected IgM absorption, it has been the fit has been brought down to 800 angstrom. So we see here when the fit of the continuum, the red line, then the cyan region is the region where the expected ionizing photons are coming from. And we see that on the panel above, the spectral region is in accordance with the continuum, and this suggests an escape fraction of 100%. And the lower panel, the spectral region there shows zero flux. So in that case, we have an escape fraction of 0. So this was done for each quasar individually. And on the right side, we see the stacked spectrum of all the 1,600 more or less quasars. And we see on the right plot lower panel that for all of them down to absolute magnitude of minus 26, the escape fraction is of the order of 75% at least. So at the same period, more or less, a noticeable escape fraction was being confirmed also for fainter IgN, but at lower redshift. So in 2018, we have decided to do a survey of faint IgN in the redshift range between 3 and 6. So we have obtained here, I show some example of the spectra that we have used. The upper panel is with LDSS3, this is at Magellan, and below is MODS, MODS spectrum. MODS is at the LBT, the Large Binocular Telescope in Arizona. And the panel on the right shows the method, which is more or less what Cristiani did in 2016. So here is very similar. So like the blue vertical line is the location of the break at 912 Armstrong. And then the green region is above the break, and the magenta region is the region where the ionizing photons are supposed to be emitted. So the red horizontal lines in each of these regions is the mean value for each region after a 2 sigma clipping. So, and the escape fraction is the ratio between these two mean fluxes. So, as I said, we have done a systematic survey. The redshift range we have used was 3.6 to 4.2. So the redshift interval, in this case, it was used as a good compromise between minimizing the IgM absorption and allowing observations from ground. And the facilities we have used, there are three. We have used instruments at LBT, at VLT, and at Magellan. So here are the results. And you see that all the sources that we have observed, they show a significant escape fraction that ranges from 44% to 100%, with a mean value of 74%. So this is in agreement with the results obtained by Christian in 2016. And as you can see on the plot on the right, there seems to be no significant trend. You know, like it doesn't seem that the escape fraction is evolving with luminosity. So at this point, we had to calculated the total hydrogen ionization rate. So here you can see that the various signs on the top is the UV background calculated based on various indicators, and the colored squares are the ionization rate as calculated based on various luminosity functions. So the magenta square is the UV background as produced assuming the luminosity function by Giallongo et al. 2015, and an escape fraction of 75 down to an absolute magnitude of -18. And as you can see, AGN in this redshift range can produce up to 85% of the UV background. But choosing different luminosity function, the spread is very high, as you can see from the other colored squares in the plot. So at this point, it is crucial to study the luminosity function and measure the escape fraction. So we're starting with the luminosity function. So one of the first indications of steep luminosity functions for redshift higher than 4 was by Glickman et al. In 2011. And you can see also how in the plot how the steepness has changed between, from candidates to a spectroscopically complete sample. So, but nevertheless, the steepness was above what had been thought at the time. And so Madao has included these values. So on the panel on the right, we see the emissivity as presented. The dotted line is by Hopkins in 2007, considering the luminosity functions that were fading in at redshifts above 3, and then by adding though the blue point by Glickman and the green points based on the Giallongo luminosity function, the simulation showed that if confirmed, they could strongly contribute to the ionizing UV background. So again, at this point, we have decided to do a luminosity function at redshift 4. We did the pilot program with IMACS. So in this case, in order to select our candidates, we have used 3 criteria. First, you had color selection for identifying faint AGN using photometry from the literature. Then again, from the literature, we took the photometric redshifts presented in the Cosmos 2015 that are supposed to be very precise. And we also used X-ray emission. Our final sample included 92 sources with a magnitude in the I band of 23. And after our spectroscopic campaign, we had 36 sources with robust redshift determination. And I show some examples here on the left panel. At that, we only managed to spectroscopically confirm half of our sample. As you can see, 53% of our sample still needs spectroscopic confirmation. But nonetheless, we learned some valuable lessons. So that's, for example, here on the lower plot, you can see the green points are the sources that have confirmed redshifts in the redshift range that we're interested in, between 3.6 and 4.2. And you can see that half of them are outside the color locus. So color selection is incomplete. And then also the X-ray selection is incomplete, since only 8 of the AGN selected by color and photometric redshifts actually presented X-ray emission. So based on that sample, we have calculated the faint end. And here we have considered 13 AGN with an I-band magnitude of 23 limit. And without completeness correction, like just taking the number and dividing by the volume, we get the blue squares that you see here in the plot that nicely fit in the Glickman luminosity function, and they put the better constraints on that region around the -24 absolute magnitude. So these two blue points are the lower limit, let's say, for the luminosity functions, like because it includes no completeness correction, so it's just numbers divided by volume. So as you can see, all the luminosity functions that are under those blue points are under predicting the AGN numbers. So, and as you can see, only the Gianlongo et al. 15 points and the Parsa luminosity function is in line with the points that we have calculated. We decided to go for even higher redshift, and in this case, we have used the candles with selecting galaxies brighter than 27 and with a photometric redshift higher than 4. So here are examples of the spectral energy distribution fittings. And here the result was 32 candidates with X-ray detection in various X-ray surveys of different depths. So again, here you can see the upper panel shows the luminosity function at a redshift of 4.5, and below it's at 5.6. At the upper panel, we see that the luminosity function calculated by Gianlongo et al. In 2019 is in accordance with the points that we have calculated at 4.5. And at the redshift of 5.6 is a factor of 3 higher than the luminosity function presented by Parsa et al. In 2018. So, oh, sorry. So at that point, again, now recent surveys, they show that even then the estimates were high, but the UV luminosity functions, as they are being now calculated based on the James W. Webb results, confirm the steepness of the luminosity function, and actually they show that it could be even higher than Gianlongo 19 and Parsa 18 in both redshift range. So as you can see, the red points are above the cyan points. So this means now assuming the luminosity function by Gianlongo et al. In 2019, an escape fraction of 75, the AGN can produce up to 80% of the UV background. And again, based on the Harikane et al. Paper of 2023, with near-spec spectra. So they confirm these results, and they're in line. So AGN could be major contributors. And in the future, it is crucial to study the luminosity function at redshift above 5. So now let me pass to the QUBRICS survey. We're still looking for AGN. This time we want to find the characteristic of the survey is to find new and bright high redshift quasars. So brighter than magnitude 18 and higher than 2.5 redshift. So the reason for this is simple. It's like in the future, we are building all these extremely large telescopes. Most of them are going to be in Chile. At least 2 of them are going to be in Chile. So we're going to have the science that can be done by these big facilities currently, or at the time that we started the survey, it was hampered by the lack of luminous targets in the south with respect to the north. So taking advantage of the various databases that were being created during that time, we started to search for bright quasars in the south that can be used then for several other searches, science subjects. So at the beginning, the selection algorithm that was used was a canonical correlation analysis. So we started with machine learning formulas. So we used as a training set all known quasars from the literature. We used information from Gaia, proper motion information from Gaia to exclude stars. And then it was an iterative process because so as we would observe our candidates and confirm new quasars, then we would put these new quasars in the training set to better train to better select our candidates for the next run. So our initial sample contained like 1,500 candidates, and the completeness was 90% based on known quasars. And the success rate after the first spectroscopic follow-up was of the order of 80%. So then as the campaign progressed, also the selection algorithm evolved. We are now using the probabilistic random forest. So the advantage of this method is that it can account for missing data because, you know, as you probably know from the surveys, you know, there are sources that could have magnitudes in some bands and not all the bands that are required. So here we have input from 4 catalogs. We use magnitudes from SkyMapper, from Gaia, and then we take infrared magnitudes from TUMAS and magnitudes from AllWise. So here we show on the panel on the right how the completeness and the contamination of our sample, and as you can see, the completeness is at redshift above 2.5 is of the order of 85%, and the contamination is of the order of 20. And as we go to higher redshifts, the contamination is lower, but also the completeness is lower. And for this reason, and this was mainly due to the small number of existing bright quasars with respect to the other kind of sources that we can find in the sample. So in order to improve our training sample, we have decided to use the synthetic data. So we have created synthetic SCDs, and each SCD is characterized by 3 parameters. So F is the fractional contribution of the air bump, infrared bump with respect to the UV bump. Then the sigma is it shows accounts for the extinction, and then there's the redshift, the spectroscopic redshift. So as we can see here, then there are 3 steps in order from an SED to become like, magnitudes in a database. So first, the SEDs were redshifted in the observed frame and multiplied by the IGM transmission. Then they were multiplied by the survey bandpass to obtain instrumental magnitudes. And then the instrumental magnitudes were resampled in order to reproduce the distribution of the sample. So as you can see in the table above, the recall. So recall is how many of the relevant instances you can actually tell what they are, like you classify them correctly. And precision is how many of the relevant instances that you have in your sample are actually the sources that you're looking for. So we can see that with real quasar spectra only, the precision is high, is of the order of 82%, but the recall for redshift above 2.5 is of the order of 70%. So by including the synthetic spectra, the recall goes up to 87 and 98% for redshift ranges above 3. Of course, this way we pay a bit with the precision, but the thing, so here is a game of optimizing, like finding all of them, and it's an optimization between, yes, like having a high completeness and how much contamination you're willing to take. So the follow-up of our candidates has been done with various instruments on various telescopes. So at Magellan specifically, we have used at Las Campanas specifically, we have used the Wi-Fi CCT that was at DuPont, IMACS and LDSS3 at Magellan, and then we used EFOSC at NTT and Dolores at TNG. Here on the plot, you can see the sources, confirmed sources with a redshift above 2.5. Blue points are generally found in the literature, and the red points, which as you can see are like half of them, are based on the QUBRICS survey only. So from all the candidates that we have observed, 75% are AGN. So our main, let's say that our main contaminants are AGN nonetheless, but they're just at lower redshift than 2.5. And then for the updated algorithms, we are expecting a high completeness and a high purity. So based on the dataset that we created, the spectroscopic dataset that we have created during the QUBRICS survey, this time we have tried to calculate the luminosity functions, but at the bright end. And here we have identified 58 quasars with an I magnitude brighter than 18. Always the redshift range is between 3.6 and 4.2. So as you can see, the blue points, the 3 blue points are the ones from our survey, and we are the first one to extend the sampled absolute magnitude to an absolute magnitude of minus 29.5. So we actually do find the brightest quasars that are out there. And based on our derived bright end slope, we concluded that bright quasars could be significant contributors to the ionizing background. So always based on the spectroscopic data selected for QUBRICS, we have also calculated the space density at redshift 5. Here we have used 14 spectroscopically confirmed quasars at a redshift range between 4.5 and 5. And as you can see, the space density that we found is like 3 times higher than previous determinations. So at the time during the survey, we also had some unexpected results. So at the beginning, a big fraction of our candidates, like 10–15% of the sources that we were observing, they had this weird absorbed spectrum that you can see on the left. Only based on that optical part and saying that this was like a Lyman limit, the tentative redshift was 4.35. But doing follow-up observations with fire, we see that these interlopers were actually broad absorption line quasars, specifically having iron absorptions. They're called philobulbs, and their redshifts were lower. They were, the redshifts were of the order of 1.5 to 2. So this was surprising because we had, at the beginning at least, we had a lot of these sources, but these kind of sources, they only account for 1% of the general quasar population. So, but since their SCDs are very similar to redshift 4 AGN, we were not able at that point to exclude them. So anyhow, this is a very good method again to select these sources that are very rare in and they can be used then to do other studies. We also managed to achieve our goal, and we did find like the brightest, some of the brightest quasars currently known in the southern hemisphere. Here I show example of these spectra. We have 2 sources with redshift at 3.90, above 3, close to 4, and the brightest one is with an eye magnitude of 16.2. So another thing that we can do with the results of our survey, so based on our results, we presented the golden sample. So the golden sample is a sample of very, very bright quasars in order to do the Sandage test. So based on a study by Liske in 2018, at that time, you had to consider like 4,000 hours of ELT time were necessary in order to complete the Sandage test. But with the sample of quasars that we presented, this budget time would go down to 2,500 hours. So very, very recently in 2023, we also presented a paper, by Cristiani et al., where we have searched the Gaia database for low resolution spectra. And after combining them with our photometric data, we managed to have a secure redshift determination. So, and here we show example of these sources. And here also it's an histogram of the various redshifts. So based on that, we have selected 7 sources with an I-band magnitude brighter than 17.5 and a redshift range between 3 and 5. And now, based on these sources, it is possible to carry out this experiment in only 1,500 hours with a spectrograph like Andes that is being projected for the ELT. So this is all work in progress. As I mentioned, we keep updating our algorithms. Now we are adding new recipes in order to not only to have to select the candidates, like, because so far it was saying like how many are above 2.5 and what are below 25. But now we add recipes to calculate predictions for the exact redshift of each source. Currently, we have enough new redshift determinations for quasars in the redshift range between 3.6 and 4.2 that could warrant the revision of the luminosity function. We are tuning, since we have been very successful at the redshifts above 2.5 and 3, we're now tuning our algorithms in order to extend the search at redshifts above 5. This way we would repeat the escape fraction analysis at such redshifts. And then we have ongoing programs with X-Shooter, and more recently also we would like to use Espresso in order to study the super bright quasars that we have already discovered. And this is all from me. Thank you very much.
Thank you very much, Konstantina. It's a very interesting work.